In this video, I'm going to introduce the basic ideas in classical scalar field theory. All right, so to tackle classical scalar field theory, we're going to build off of Lagrangian mechanics. So we're going to start with Lagrangian mechanics and build it up, and that's going to form the basis of our framework for classical scalar field theory. And so recall in just normal classical mechanics, we have this object called the action, which we write as S, and it's the integral of the Lagrangian with respect to time. And our Lagrangian is this object, which depends on the energy in our system. And we think of it as the function which sort of defines what's going on in the system that we happen to be studying. This works great for classical mechanics, but we're going to want to be doing not just classical scalar field theory, but we want this to be relativistic. And therefore, we want to be treating space and time on equal footing. Whenever you want to deal with any sort of relativistic theory, one of the key things that you should always be having in the back of your mind is that space and time should be treated sort of the same. This action, as it's written, looks like it's treating time as sort of special. It's this integral with respect to time specifically. So it's treating time differently than our other coordinates. And so in field theory, we're going to rewrite this and our field theory action still we're going to use S, and it's going to be the integral over something where we often use a curly L, and this is going to be a Lagrangian density. And then we're going to integrate over space and time. So often actually we'll just write this as d4x here, where the 4 is representing over all 4 of our space-time coordinates. And so I haven't really done anything. I've just defined this new thing called the Lagrangian density. And then I know that my action now is something that seems to be treating space and time on equal footing. I'll note that I'm calling this a Lagrangian density now in order to distinguish it from classical mechanics systems. But ultimately, people often just drop the word density and just call this Lagrangian. And if you know you're doing field theory, then you know that the Lagrangian actually is a Lagrangian density. Okay, so that's how we're turning our action sort of up a notch to work with relativistic theory. Okay, so just like in classical mechanics, when you have a Lagrangian, your Lagrangian is going to depend on the system that you're dealing with. The simplest example of a Lagrangian that we can deal with in field theory, or the simplest field theory, I guess, we can deal with, is one that has just one scalar field. So a simple field theory has just one scalar field. I'll define that in a second minute. But before I define what I mean when I say scalar fields, just to give you a little bit of what's ahead. So in particle physics, what's going to happen is for each of our different types of particles, there is going to be a field associated with it. So you can think of there being a field associated with the electron, a field associated with each quark, right? And these particles we think of as being excitations of these fields. And so what I'm going to do here when I say I'm dealing with a simple field theory, I'm going to deal with something where I have just one particle is one way to say it. We have just one field. So it's like we have all that exists in the universe that we're dealing with is this one particular type of field, which you can think of in particle physics as being associated with a particular particle. And this particle is such that the field that it's associated with it is a scalar field. And so we're doing a very simple model here. So we're simplifying our system and dealing with the simplest type of system that we can imagine. Okay, so what is a scalar field? So we'll often use phi or other Greek letters, but in this example, I'm just going to use phi. This is something that's going to be a function of t, x, y, and z. So a scalar field is a function of space and time that assigns a scalar value to every point. So a really simple example of this is a temperature field. So in this room, I could go around with a thermometer and measure the temperature at every point in the room. And I could do this at every instant in time. Okay, I'd need a bigger machine if I was actually doing it. And at each point, right, I'm assigning a value. At this point, the temperature is 68 degrees. At this point, it's 67.5 degrees. At this point, it's 67 degrees. So I'm assigning a number to each point in space. And then, of course, as the day goes on, as time passes, those values at each point might change as the sun comes out and the room heats up, right? And so the value changes. And so when you think about a scalar field, just a classical scalar field, something like this is exactly what you can think of in the back of your mind, right? It's something where you see a number living at each point in space. This is different from a vector field. A vector field maybe actually is more familiar to you in that you've dealt a lot with electric fields and magnetic fields. These are objects that assign to every point in space a vector, right? With the electric field, you're imagining a little arrow associated with each point in space, right? There's a vector quantity at each point. A scalar is simpler than that. We're just putting a number at each point in space-time. Okay, so we want to study a system where all we have is one scalar field, and we want to think about how this one scalar field is going to behave. So let's try to write down our Lagrangian density. And I'll put density in parentheses, right? Because as I said, once you're dealing with field theory, people often don't say the word density all the time, but that's actually what they're talking about when they say Lagrangian. Specifically, it's a Lagrangian density for a scalar field. So our Lagrangian density, again, is going to be something that maybe I should use like a curly K, that's a kinetic energy density minus some sort of potential energy. So the kinetic energy piece is going to look like this. I'm not proving it to you in this video that this is a reasonable thing to do, but it hopefully feels reasonable. So kinetic energy terms in general have to do with derivatives, right? Your kinetic energy is 1/2 mv squared. It's the derivative of your position. So our kinetic energy term in our field theory is also going to have to do something with derivatives. And we want this to be a relativistic theory, so we can't just have time derivatives. So we're also going to have these spatial derivative terms. And that therefore we're respecting the symmetries of our system explicitly when we write down this term. So this is what our kinetic energy term is going to look like. And in field theory in general, your kinetic energy terms are always going to look something like this. You know, they'll look a little bit different if my field is a vector field, but in general, they're all going to have this same sort of form. Now, the potential energy, this is going to depend on what types of interactions I have for the particular theory that I'm studying. So ultimately, when we do more advanced things, when we have more than one type of field, then we might have two different fields that interact with each other. And remember, again, these fields are sort of associated with our particles. So if we know that an electron and a positron, they interact with each other. So in our field theory, those fields should have some term associated with those interactions, right? If the two things totally ignore each other, like a photon and a neutrino, the neutrino is electrically neutral, it doesn't interact with the photon, so there should be no term associated with the interaction between them. But for things that interact with each other, that have some force, right, there should be a term associated with each of these interactions. And so we can have all sorts of things that we write down. Here we just have one scalar field. So the question is, does this field interact sort of with itself? And we want to do something a little bit interesting. So a simple interaction that we could write down is just U equals 1/2 sigma, where sigma here is just some constant. And the 1/2 is a convention that's pulled out of our constant just for convenience. And then phi squared. So this we would call, this is the phi squared theory, where we just have one interaction term, which is phi squared. We could have more terms like phi cubed or phi to the fourth, and those would just be more complex systems where more interesting things are going on. But this is a term that we could write down that would be our simplest term. And so our Lagrangian density is 1/2 d mu phi minus 1/2 sigma phi squared. So this is an example of a very simple Lagrangian with one scalar field with one type of allowed interaction, so one energy term. And it's important to notice that this thing is a Lorentz scalar. Right? Lorentz scalars are objects where all of our indices are contracted, so we don't have any free indices left over. And we are always going to want our Lagrangian densities to be Lorentz scalars because that guarantees that the symmetries of our system are respected. That guarantees this physical system that we're dealing with is going to have Lorentz symmetries, which we want all of our relativistic. If this is a relativistic theory, it should have the Lorentz symmetries. And so whenever you write things as a Lorentz scalar, you know that that's explicitly going to obey the symmetries because this thing is going to look exactly the same in all reference frames, right? It's a Lorentz, that's what it means to be a Lorentz scalar. And so this is good, and this is what we're always going to want. Okay, so let's actually use the Euler-Lagrange equations to solve for the equations of motion for this particular example, right? This is the simplest example we can have of a theory with one scalar field. So we're going to use Euler-Lagrange to solve for equations of motion of our system. That's always what we want to do in physics is we want to find the equations of motion and then we solve them given certain initial conditions, for instance. So first of all, what does our Euler-Lagrange equation look like in this field theory? So our relativistic Euler-Lagrange equation. Because again, the Euler-Lagrange equation has that like time derivative that's pulled out. This thing doesn't look like it's treating space and time on equal footing. So our relativistic generalization of an Euler-Lagrange equation looks like this. This is our Euler-Lagrange equation. And since we just have our one scalar field, we just have one Euler-Lagrange equation. Again, if we had a more complicated theory where we have different types of fields, whether they all be scalar or maybe we have vector fields, then we would have an Euler-Lagrange equation for each field. Here we just have one field, we just have one equation. This first term right here probably looks a little weird to you, like what does this mean? But this is the same thing as taking a derivative with respect to x dot, right? Where we just treat d mu phi like a thing that we're taking derivative with respect to. And I think actually, without me even just saying more words, let's just work through this and see in this specific example how taking this derivative with respect to d mu phi works. If you like, I'll mention one thing you could do to work through this is to pretend for a minute, just call d mu phi psi. Call it something different and work through this. And then at the end of the day, replace psi with d mu phi and uh, and and you'll have done it. Because that's all we're really going to do is we're going to treat d mu phi like it's its own thing. So if we're taking the derivatives of this Lagrangian, it's a little bit, to be really careful, it's nice to first rewrite it as maybe where I've just written my kinetic energy term. I've lowered one of the indices, so they're both lower. So then when I take the derivative, I'm taking the derivative with respect to d mu phi, which is lower also. It's just kind of nice to do that to make sure you don't mess anything up. Okay, this is our Lagrangian. So let's do this derivative that I've underlined in red. So I want to take a derivative with respect to this whole quantity d mu phi. Sorry, and I made a typo up above. This should be a new right here. Okay, I want to take the derivative with respect to d mu phi of this thing. I see these two terms here, which look like a d mu phi, except our indices have different names. So remember these indices run 0, 1, 2, 3, or t, x, y, and z. This thing underlined in blue only matches one of these things underlined in green if our indices match. And so when we take this derivative, so g beta nu is just a constant, right? We don't have to worry about those. Oh, what just happened there? Okay, this, maybe I'll write this as an aside, right? So d, d, d mu phi of d nu phi is equal to delta, Kronecker delta, nu mu. So this is the rule I'm going to use. It says, right, because if I'm taking a derivative, let's forget about taking a derivative with respect to something that's a derivative. If I want to take the derivative of some function with respect to x, or with respect to my coordinates in general, I have to, if I want to make sure that when I take a derivative with respect to x, I'm only finding my x's. And if I want to take a derivative with respect to y, I'm only my y's are the ones that I'm taking a derivative with respect to. And that's what this Kronecker delta is sort of doing for me. Stare at that for a little bit and convince yourself that that makes sense, that that's what we're doing here. Because you only want it to be not zero when these two things agree. And that's what the Kronecker delta does for us. So we're basically going to do a product rule here and first take a derivative with respect to this first guy. And we get our Kronecker delta nu mu. And then the other guy goes along for the ride. And then we have a second term where we take a derivative with this second one. And then now we get a Kronecker delta with our beta on top. All right, and then this second term doesn't have any derivatives of phi, and so that just goes away in this derivative. Okay, let's think about these things that I've written down. So we can immediately use our Kronecker delta to, we can combine these two things. We do our sum over nu, and that makes my G become beta mu d beta phi. And I'm going to do the same thing on my second term, where I have a Kronecker delta, and I'm going to combine it with my G. So now I have plus 1/2 G mu nu d nu phi. And then I use my G to raise my indices on both of these terms. And then I notice both my terms are the same. So this is just d mu phi. Yay. Okay, so we end up with this nice simple thing that actually, if you go back to the beginning, if you look at this thing, or even if you go before that, we had something that was like a derivative squared, d mu phi. And so sort of taking the derivative, we did this in this really long, explicit way to make sure everything worked out the way it should, but actually the answer we got is the one that you could have maybe guessed from your calculus intuition before. Okay, so now that's the first part of our Euler-Lagrange equation. We also want to deal with this second piece of our Euler-Lagrange equation. That's a lot simpler, right? We're just taking the derivative with respect to phi. And just like always, when I take the derivative with respect to phi, I treat phi and the derivative of phi as totally separate things. So this first term in our Lagrangian just goes away. So dl d phi only has the piece from the second term in our Lagrangian, which now is minus phi, sigma squared phi. Okay, so that's our second piece. So if we plug these into our Euler-Lagrange equations, then we still have this derivative out front, and we plug in this guy, and then we have two minus signs, so end up with a plus sign, sigma squared phi. Okay, so this is the solution of our Euler-Lagrange equation, and these are our equations of motion. For our scalar field. When we just have a scalar field with just that one type of interaction turned on. And now the equations of motion always, when you're doing physics, the equations of motion are simply a set of differential equations. This is really it's a differential equation. Maybe a hard one, but it's one that we can solve. And the solutions are just our plane waves. So you can check for yourself that the solution can be written as A, where A is some integration constant. Ultimately, it's the amplitude of our waves, cosine, and then some set of constants plus some phase. Right, so the amplitude and the phase, ultimately, these would depend on if we're thinking about a specific scalar field, a particular instance of a scalar field, and we want to see how this scalar field behaves. Just like whenever we do any physics, we need some initial conditions, and those are going to determine our amplitude and phase. So these are determined by initial conditions. And then K mu, this should look like a wave number. This is a 4 vector of constants where the spatial parts of them, their magnitude is 2 pi over lambda, where lambda is our wavelength of this wave. And you can check all of this by plugging this solution back into our equation, and I encourage you to do that to convince yourself that indeed this is an allowed solution. Okay, so that is a very brief introduction to classical scalar field theory, right? Here we've made things relativistic explicitly, but everything here is still classical in that there's no quantum mechanics going on yet. We haven't enforced any axioms of quantum mechanics. Here we're just dealing with a classical field, a classical relativistic field. All right, thanks for listening.